Ashley Broderick, and this is Lab 3, Magnetic Field of a Bar Magnet. So as an introduction, the purpose of this lab was to measure the distance dependence of a magnetic field due to a bar magnet. And this was done using the fundamental principles that the absolute value of the magnetic field of the bar is equal to k times r to the n, and the linearization plot that the natural log of the magnetic field is equal to the natural log of k plus n times ln of r. And this allowed us to find n, and then eventually we went to use this dependence to determine the magnetic dipole moment, and this was found using the fundamental principle that k is equal to mu naught over 4 pi times 2 mu. And then the problem was to then use the experimental dipole moment to determine the computational magnetic field and compare it to the experimental magnetic field results. And this was done using the formula to the right. And the key results were the linearization of y is equal to negative 3x minus 14, mu is equal to 3.83, and the experimental magnetic field was found to be 6.45 10 to the negative 5 Tesla, and the computational magnetic field was 1.59 10 to the negative 5 Tesla, so same order of magnitude. And then throughout the rest of the lab, we'll demonstrate the methods that were then used for the experimental and computational data, and then some questions to conclude. And in this lab, the bar magnet is a model of a dipole. So the methods, one, we had to compensate for the magnetic north, so we placed our phone so that the x component was approximately 0 in the magnetic field, and then we had to find where the chip was located in the phone. This was done by finding the intersection of locations where there was a maximum absolute value of the x component and minimum absolute value of y component of the magnetic field, and the other location where the maximum absolute value of the y component and minimum absolute value of the x component of the magnetic field. We then measured and recorded the distance of the magnetic field dependence and measured the off-axis magnetic field, which is shown from the bottom picture on the right. Some data from this experiment is shown here, and the linearization that was found using this plot was y is equal to negative 3.0401x minus 14.082. And a closer look at the plot, the slope was found to be negative 3.0401, which was n, and then the y-intercept was the natural log of k, which was negative 14.082. This allowed us to find mu as 3.83, and the calculations will be shown in the next slide. So when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and this is important to make sure we are in line with the Earth's magnetic fields. And as it moves closer to the magnet, the measured x component of the magnetic field increases. The calculations used to find mu are shown here with the linearization equation, and so as said before, n was found with the slope, natural log of k was found with the y-intercept, and then by solving for k, we found that it was 7.6610 to the negative 7, and by plugging this into the equation that k is equal to mu naught over 4 pi times 2 mu is found to be 3.83. So we used this value of mu in the computational model, and the important sections of code are shown here, and this was the output diagram, and this allowed us to compare the magnetic fields of the computational and experimental values that were found to be somewhat close due to the fact that they were the same order of magnitude. And then some concluding questions. If we had not oriented the experiment to compensate for the magnetic north and instead laid out the meter stick at some intermediate angle with respect to the Earth's magnetic field, how would your results have changed? So if this were the case, then the magnetic field of the Earth and the magnetic field of the magnet would not be perpendicular, so the dot products wouldn't be 0, and the dot product in this equation shown. So this would increase the value of the magnetic field, as the results would no longer be testing only the magnetic field of the magnet, but also the magnetic field of the Earth. So they would be using the superposition principle. And then the final question, if you were to stick two identical magnets together end to end, how would your measurements differ? And this would double the magnetic field. It's because the two magnets together creates a dipole moment that's doubled, and therefore doubling the magnetic field. So in conclusion, we found that our computational and experimental calculations for the magnetic field were somewhat close, and the linearization plot allows us to solve for n and mu. Thank you.